exponential equations, okay? So that's the heading. Okay, so what is an exponential equation? Of course, I'm going to give you the definition. All right, so DEF, of course, stands for definition. The definition is going to follow. So here we go. An exponential equation is an equation, of course, in which the variable, so the variable that we're solving for, is in the exponent. Okay, it's in the exponent. The variable is an equation in which the variable is in the exponent. Okay, so yeah, so we're going to have an equation. We're going to want to solve for x, but that x will be present in the exponent, all right, of an exponential expression. All right, so we're going to develop some tools to solve these kinds of equations, all right? And one of the tools will be called the one-to-one property, all right? Okay, so here we go. So the function b to the x, so our good old exponential function, that is one-to-one. Okay, and there's a few ways to see this. The quickest way, it will pass the horizontal line test. All right. So, but in symbols, what does this mean? What is the definition of one-to-one mean? That means if b to the x equals b to the y, if the outputs of x and y are the same, then the inputs are the same, x equals y. Okay, so what I'm going to highlight right now is literally what it is, the definition of b to the x being one-to-one. It means if the outputs, b to the x is equal to b to the y, if they're equal, then the inputs were equal to begin with. That's one-to-one. All right, so that was from a few weeks ago. All right, so we're going to use this to help us solve equations. So very quickly, very quick example. If 2 to the x equals 2 to the z, just for some numbers, x and z, if you know that this is true, then you can deduce, you know for a fact, that x will equal z.
Because it has the same base?
Well, it definitely has to have the same base, yes. So if you look in the highlighted, I have b's. They're the same base, yes. Okay. If they were not the same base, we could not make that conclusion. All right, so that's it. Yeah, so actually, Saeed, I'm glad you mentioned that. In my notes, I literally have warning. The bases have to be the same. So good intuition there. So warning, bases must be the same. All right, so that's the deal. That's just one-to-one. So nothing new here, but we're applying it in the context of the exponential function. All right, so here we go. So here we're going to do the method of using like bases. So here's a new heading. Using like bases. All right, example. Solve 2 to the x minus 1 equals 2 to the 2x minus 4. That's the question. Okay, so here we go. We're going to use this. We're going to use the one-to-one property off the bat. If b to the x equals b to the y, which we have 2 to the something equals 2 to the something else, we know that the exponents themselves are equal. All right, so let me just write that very quickly. Since the bases are the same, we can what can we do? What's our deduction? We can set the exponents equal to each other. All right. We can set the exponents equal to each other and solve for x. All right. All right, so let me go ahead and do that. So the exponents here are x minus 1 and 2x minus 4. So I will go ahead and set them equal to each other. So x minus 1 is equal to 2x minus 4. All right, and now we are in a very familiar situation of just solving like linear equations. All right, this is now reduced down to solving a good old linear equation. All right, so I can leave it to you guys to work out the details, but you will get x is equal to 3. All right. All right, I'm fairly confident in everyone's abilities in solving this equation here. All right. So x equals 3, and that's going to be the answer to our exponential equation. That's the answer. And you can check, you can actually substitute in x equals 3 into this. So let me do that mentally. So if I put 3 on the left side, I'll get 2 to the 3 minus 1, which is 2 squared, which is 4. Left side is 4. What about the right side? I'll have 2 raised to the 6 minus 4, which is 2 to the second, which is 4. So you get 4 on both sides. It works. All right. So is everyone okay? Any questions on the technique? All right. Let's do one more quick one. All right, solve 5 to the 3x plus 2 is equal to 5 to the 2x. Okay, this is the exact same procedure as the previous example. Sorry. The bases are the same, so I can just set the exponents equal to each other. That's it. So 3x plus 2 will be equal to 2x. All right, and this you will get is equal to negative 2. All right. So please stop me if anything is unclear. Okay, so the fact that we had the same base on both sides in these two examples, we got rather lucky. That's like a rather convenient situation. So sometimes we have to rewrite one or both sides so they have the same base. All right, so let me write that very quickly. So it's not letting me change the font size. I don't know why. There we go. Okay, so sometimes we have to rewrite one or both sides of the equation. So both sides have the same base. Okay, so that's doable. So let's do an example. Okay, so here we go. Let's do 4 to the x is equal to 2 to the x plus 1. Okay, so the problem here is that we cannot apply the one-to-one property off the bat. We need to rewrite both sides so they have the same base. Okay, but this is not that bad because 4 is equal to 2 squared. So I can realize the left side as 2 raised to something. All right, so let me just write that. We need both sides to have the same base. Okay, and this is very easy. So all you do is you rewrite 4 as 2 squared, okay? Okay, so let me do that. So this 4, I will just rewrite as 2 squared. Okay, so this 4, I'm just gonna place this as a 2 squared. That's it. Everything else stayed as is. So this exponent of x, it's still there. All right, so just do things one step at a time. Okay, next. Now, use properties of exponents on the left side. Okay, so what can I do in this situation? I have an exponent raised to a power. I have a power to a power situation. Does someone want to maybe tell me how I can rewrite the left side?
It's 2x.
So 2x where?
On the left side, you could distribute well, you would have to multiply the exponents.
So what am I left with in total on the left side?
2 to the 2x.
Yes, exactly. So by properties of exponents, as Luke said, I can multiply these 2 exponents together, and it's the same as 2 to the 2x, exactly. 2 raised to the 2x. That's the left side, and the right side stays exactly the same. Good, now use one-to-one property, because now we have the same base on both sides. Okay, good. So we can set the exponents equal to each other. 2x is equal to x plus 1. And solve that guy, you will get x is equal to 1. That's it. All right, so I hope that's okay. So it's similar to the previous examples, but there's a step you have to do in the beginning to create like bases on both sides. All right, let's move on. We'll do another example. Another example like this. Okay, so this will be 8 to the x plus 2 is equal to 16 to the x plus 1. Okay, the problem here is that we don't have the same base on both sides, but we can make it so. Okay, so we need to rewrite both sides so they have the same base. So any ideas? How can I write both sides so they're of the same base? So do you guys want to think about that for a second? So I will just start it off. So we can write, I'm not going to answer that question just yet. We can write both sides as a power of what?
You can do it with the base of 2. So for 8, you can do 2 cubed. And 16, I think it's 2 to the 4th.
Excellent. There you go. So that's precisely what you need to do, right? So 8 can be realized as 2 cubed, and 16 can be realized as 2 to the 4th. So now you just substitute those in. So just notice how I'm being very careful with my parentheses and exponents. I'm just copying down the exponents first, and then I replace 8 and 16 as their powers of 2. Okay, so I'm just being very, very cautious. So 8, I fill in this parentheses with 2 cubed. And I fill in the right side parentheses with 2 to the 4th. All right, now I can use properties of exponents to multiply these guys together. So I will get 2 raised to the 3 times x plus 2 is equal to 2 raised to 4 to the x plus 1. All right. So from here to here, this is properties of exponents. All right, I can multiply the powers together and just be very careful with your parentheses. Remember, you need to multiply 3 by the whole quantity of x plus 2. That's why I have parentheses. And similarly, you have to multiply 4 by the whole quantity of x plus 1, which is why there's parentheses there. Good. Now, we're in a great situation. We can use the one-to-one property. So what I mean when I say that is that we can, since we have the same base on both sides, we can set the exponents equal to each other. So the exponent on the left is 3 times x plus 2. And you set that equal to 4 times the quantity x plus 1. Okay. So you can work this out. This linear equation, so this is all this is, just a linear equation. You solve for x, you will get that x is equal to 2 here. All right, so I trust you guys can take it from this step to x equals 2. Okay, so any questions? We'll get some more practicing. We'll do one more example like this. Okay, so how about this? 2 to the 5x equals the square root of 2. That's kind of interesting. So the whole point here, remember, is I need to get both sides to have the same base. So maybe you guys see it already, but let me just pose the question. So how can I write root 2 as an exponent with base 2? That's the question, because we need both sides to have the same base. Okay, any ideas?
Do you just square it and then cancel out the radicand? Or the radical?
Square. Okay, so what you said would work, I would need to square both sides of the equation though, because I can't just square one side without the other. That would work, but that would create a quadratic. There would be a, actually, that would work, I believe. Yeah. So let me try that at the end. That's not what I had in mind. But any other ideas? But I do like that. That's a great approach.
Could you put it to 1/2? Like,
1/2. Sorry, I didn't catch the whole thing.
like, could you make the exponent 1/2?
Yeah. So exactly. So are you saying I can rewrite this square root of 2 as 2 to the 1/2?
Yeah.
Yeah. Excellent. Excellent. So that was my intended method. I do want to try Jenny's way after. So square root of 2 is equal to 2 to the 1/2, of course, by our work on fractional exponents. So now just rewrite the equation. This is 2 to the 5x is equal to 2 to the 1/2. There you go. Very easy. Now use 1-1 property. And the 1-1 property means I can just set the exponents equal to each other. Good, and you'll get here that x is 1/10. Okay, so that would be the answer. So I do want to try Jenny's way of squaring both sides. So let's see what happens there. So I will get 2 to the 5x squared is equal to radical 2 squared, which is 2. So I squared both sides. Now use properties of exponents on the left. I will get that 2 is equal, I will get 2 to the 10x, yes, is equal to 2 to the first, which you get 10x is equal 1 and x is 1/10. Excellent. Yeah, so that works. Very cool. Very cool. So this is an alternate method of solving this guy. Alternatively, you can square both sides of the equation and get rid of the root. Excellent. Alternative method. Of squaring both sides. Very cool. All right, so that's all I have for this section. All right, so you'll have a few of these on the homework. They're going to be very similar to what we just did. Good. So now we're going to just solve exponentials using logarithms. That's the next heading here. Okay. Let me just write that new heading. Solving exponential equations using logarithms. Okay. So just talk about this quickly. Okay, right. Yeah, so we were in a nice situation before where it was possible to write both sides as the same base. Sometimes that will not be possible, okay? So let me just write that. So sometimes it will not be possible to write both sides of the equation with the same base. Okay, and we're gonna look at that instance in a second. So what do? Well, in this case, we use logarithms. All right. So I will demonstrate, of course, how to do this. All right. So that's why we need this method, because sometimes you can't write both sides as the same base. Sometimes it's just not possible. Okay. So here is an example. 5 to the x is equal to 21. Okay, so I think you guys can maybe see that I can't write 21 as a power of 5, and I can't write 5 as a power of 21. It just doesn't work that way. So we need a different method, okay? And what we do is we will apply a logarithm to both sides, and the logarithm you do is the base of the term that has the variable in the exponent. So you do log base 5 of both sides, all right? So let me just write that. So if we apply log base 5 to both sides, okay, why do we want to do that? Because then we can bring the power of x down. Oh, and actually I wrote this incorrectly. It should be 5 to the 2x, excuse me. 5 to the 2x, I apologize. 5 to the 2x equals 21, yeah. Okay, so if we apply log base 5 to both sides, we can bring the power of 2x down as a coefficient. Okay, so do you guys remember that property? It was called the power rule. So let's just see what that looks like. So I'll have log base 5 of 5 to the 2x. So that's me applying log base 5 to the left side, and I need to also apply it to the right side. I'll get log base 5 of 21. Okay, so the whole point of using logarithms here is now I can use that power rule and bring this power of 2x down. That's the whole point. So this will be 2x. The 2x now comes out as a coefficient. This is 2x times log base 5 of 5 is equal to log base 5 of 21. Okay, so this is so from here to here, this is the power rule. Okay, this is from last class. Very good, very good. Now we didn't need to use base 5, but the reason why we did is so that this factor will be 1. That was the point. Remember, the power rule would have worked no matter what log base we used, but to make it a little nicer, we use log base 5 so that when we bring the power down, this reduces to 1. Okay, so that's 1. So this is now 2x is equal to log base 5 of 21. There we go. And now we have 2x is equal to log base 5 of 21. Divide both sides by 2 to isolate x, and you're done. So x is log base 5 of 21 divided by 2. Okay, so please do not use any calculators. Don't write the decimal expansion of log base 5 of 21. That's just not necessary. It's just going to look messy. Just leave it in this nice closed form. All right, this is a totally acceptable and legitimate answer. All right, so please don't use decimals. Okay, so any questions? So just please stop me if you have any questions. All right, we'll do another example. All right, so we'll have 2 times 3 to the x minus 5 is equal to 12. Okay, so we can't just apply logs to both sides just yet because we have this 2, this coefficient of 2 hanging out in front of the exponential. But we can get rid of that very easily just by dividing both sides by 2. All right, so let me write that. So we need to first isolate the exponential on the left side, okay? Exponential. And we do that just by dividing both sides by 2. That's all you need to do. So if I divide both sides by 2, I will get 3 to the x minus 5 is equal to 6. Okay. So I hope that's okay. Just divided both sides by 2. Now you need to look at the base of the exponential that has the variable in the exponent, and you take log base of that base. So here, really what I'm trying to say is we need to take log base 3 of both sides, because that's the base of the exponential. So remember up here, we took log base 5, because the base was 5. Now let's do 3, because that's the base. So let me write that. So now take log base 3 of both sides. Okay, so I will get log base 3 of 3 to the x minus 5 is equal to log base 3 of 6. Good. Now use power rule. So by power rule, I mean I would just like to bring down the exponent of the log input out as a coefficient. Okay, so this will be okay. So you have like a binomial, and you're taking that out as a coefficient. So just use parentheses. So it'll be x minus 5 times. All right, so just kind of be cautious with your parentheses. All right, so bring that out as a coefficient, and what's left is just log base 3 of 3. Okay, and this is still equal to log base 3 of 6. Good. And the whole point of using log base 3 was so that this factor of log base 3 of 3 will come out to 1. That's why we took log base 3 and not just an arbitrary one. Good, so that's 1. So this will come out to x minus 5 is equal to log base 3 of 6. And now you just need to add 5 to both sides to isolate x. So so the final answer, x is equal to log base 3 of 6 plus 5. Okay, so again, please do not type this into a calculator. Just leave it in this closed logarithmic notation, right? That's much more preferable. Okay, good. So I'm just going to type out the steps, okay? Because I feel like there's a lot of things going on. Let me type out the steps. Okay. Steps. So step 1, isolate the exponential on one side of the equation. Okay, that was when we divided both sides by 2. So you want to isolate the exponential. Apply log base b to both sides of the equation, where b is the base of the exponential from step 1. Okay, so that was when we applied log base 3 to both sides, because 3 is the base of the exponential. Good. Last step. Apply the power rule of logarithms. Solve for x. That's it. Okay, and power rule is when I bring down the exponent of x minus 5. And that's it. All right, very good, very good. All right, so any questions?
Just out of curiosity, can you use the that method, like the logarithmic method, to solve the former problems, like the 2 to the 5x equals square root of 2?
Absolutely.
Cool. So this is like the definitive method.
This will work for everything, but it's just a little lengthier. But yes, this will work for everything. So like what you said, 2 to the 5x equals square root of 2, the log base you would apply to both sides would be log base 2, because both sides are base 2. But yes, this is kind of like a fail safe method. It'll work.
Got it. Thank you.
Yeah. Good. Okay, good. So that's exponential equations for you. You know, they're really not that crazy, I don't think. So now we will move on to logarithmic equations. Okay, so let me write that, and then I'll of course define it. So, so the next heading, the next thing we'll do, logarithmic equations. Okay. Okay, so definition. What is a logarithmic equation? I'm sure you guys can guess, but let me just be very formal here. So a logarithmic equation is an equation where the variable is inside the input of a logarithm, is inside the input of a logarithmic function. Okay, so just like with the exponential equations, the variable was in the exponent. Well, here, logarithmic equations, the variable will be inside of the logarithm. All right. Okay, so I need to just write a warning about this. So just quick warning, and everyone should definitely have this in their notes. So after solving a logarithmic equation, you must make sure that your solutions don't create a negative number inside the input of the logarithm. Okay, if it does, you reject that solution. So definitely get this down in your notes. Very important. And I would also like someone to tell me, why is this a warning? Why am I even writing this? What is up with the logarithm that is, yeah, so what's the property of the log that's making me write this warning? Why do I need to reject a negative, anything that will create a negative number in the input? So any ideas? Why is a log of a negative number bad? So what do we know about the domain of the logarithm? What are all the permissible or acceptable x values to plug into the logarithm? What's the domain of the logarithm? Any ideas?
0 to infinity?
Yes. So the domain of the log is 0 to infinity, which means it's all the positive numbers. Okay, so the logarithm cannot take in a negative number as an input. Okay, so that's why we need to check our solutions to make sure they don't create a negative number inside the input. All right, it's like when you check a rational equation and you check the solutions there to make sure you're not dividing by 0. It's like the same idea. You need to make sure of your domain. You need to be careful with your domain. All right, so we will get to that. I think I have an example of that. If not, there's one on the homework. All right. Okay, so here we go. So the first thing will be using the definition to solve. Okay, so let me just recall the definition of the logarithm. Recall that log base b of f of x is the same as, oh, sorry, excuse me. Log base b of f of x equaling c, equals c, is the same as, remember when we convert from log to exponential form, this is the same as b to the c is equal to f of x. Okay. So that is just quite literally the definition of the logarithm. We're converting from the log form to exponential form. Okay, so we're going to use this to solve equations. So here we go. Example, 2 times ln of x. All right, so 2 times natural log of x, that's what ln is equal to 14. Okay, so we need to, so in order to use the definition of the logarithm, we need the coefficient of the log to be 1. And currently, we have a coefficient of 2. So how can we get rid of that? Well, you can just divide both sides by 2, okay? So that's the first step. You need to isolate this logarithm. Okay, first, isolate the logarithm. By dividing both sides by 2. Okay, so that will give you natural log of x is equal to 14. Sorry, natural log of x is equal to 7. Yes. Okay, good. Now I want to just rewrite this in exponential form. Now, rewrite in exponential form. Okay, so recall that ln of x, that's shorthand for log base e. So this will be e to the 7. E to the 7th is equal to x. And that's the answer. You're done. Okay. Okay, so quickly, just again, why is e here? That's because ln is shorthand for log base e. All right, good. Let's do another one. So these aren't really that bad. So let's do 2 times log of x plus 1. 2 times log of x plus 1 is equal to 12. Okay, so this is the same exact deal. We need to divide both sides by 2 to isolate the logarithm. Okay, so this will be log of x plus 1 is equal to 6. Okay, good. Next, recall that log of x, remember, log of x, that's when there's no subscript, that's shorthand for log base 10. Okay, good. So there really is a 10 understood in the subscript. Good, now rewrite in exponential. Okay, so rewrite. So which one are we rewriting? This one, this highlighted one. So this will be 10 to the 6th is equal to x plus 1. And we're not done yet because x is not isolated. So just subtract 1 from both sides. So x is equal to 10 to the 6th minus 1. There you go. Okay. So any questions on what I'm doing here? All right. Do I have any more? Oh, okay, yeah. I have one more that's just a little different. Okay, so I will do the last example under this heading, if no one has any any questions. Okay, so here we go. How about log base 2 of 2 plus log base 2 of 3x minus 5. And that will be equal to 3. I don't know why I put a 2 inside of this logarithm because that's just 1. So okay, I'm going to change that slightly just to make it a little more interesting because this is just 1 if I keep it 2 here. So let me change the input to 3. I apologize. So this will be log base 2 of 3. Okay, excuse me on that. Okay, so there's a few things you can do here. First of all, to use the definition, you need 1 logarithm on the left side. We have 2. So does anyone see any properties we could use to make 1 logarithm on the left side? So
They use product rule though.
product rule. Is that what you said?
Yes.
Yes, product rule indeed. Yes. So let me just write that. We need, good. We need to make it so only 1 log is on the left side. Yeah, because we can't use the definition of the logarithm if there's two, okay? If there's two logarithms. Okay, so use product rule on left side to condense. Use product rule on left side to condense. Good. So this will now be, the left side will be log base 2 of 3 times 3x minus 5 is equal to 3. All right, so I just, I multiplied 3 by 3x minus 5. That's the product rule. Good, now use the definition. So now we're in good shape. All right, well, I use the definition, but I just actually rewrite an exponential. I'll write in exponential form. Okay, good. So we have the base of 2. So just use the conversion from log to exponent. You will get 2 to the third is equal to 3 times 3x minus 5. Okay. And yet again, we are now at the point where we're just solving a linear equation. Okay. All right, so what's this going to be? So let's actually do this one. So 8 will be 9x minus 15, which is now 9x is equal to 8 plus 15, that's 23, I think. 9x is equal to 23. Yep. And now just divide both sides by 9. So x will be 23 over 9. Okay. And that will be it. So any questions on what we did here? This one was a little more involved because we needed to get the left side to be one logarithm. Okay. So please stop me if anything is confusing. All right, good. So we are now at the last thing for tonight, the last method of solving logarithmic equations. So let me just start a new sheet here. Okay, so the final heading tonight will be using the one-to-one property. Okay, so recall that log base b of x, this is a one-to-one function, okay? Log base b of x is a 1-1 function. So what does that mean in terms of the definition of one-to-one? Well, that is if log base b of x equals log base b of y, then we can make the definitive conclusion that x equals y. Okay. And very important note, just like with the exponential guys, the base must be the same. We need the same base on both sides, okay? So what I'm going to do is I'm just going to write out the steps now, and then we'll solve some. All right. So let me just write the steps now. All right. Steps. Okay. Step 1. So step one, use properties, sorry, some typos here. Use properties of logs so that the equation takes the form log base b of f of x. Sorry, I don't like how I wrote that. So it's rewrite, use properties of log so that the equation takes the form log base b of f of x equals log base b of g of x. Okay, that's step one. Step two is you use one-to-one property to deduce that f of x equals g of x. Okay, so once we're in the situation of step one, we apply the one-to-one property. Okay, very good. Step three, now you just solve an equation. Now you solve f of x is equal to g of x for x. Okay, so usually this will be some quadratic equation maybe, or a linear equation, which we know how to do. And fourth, and most important, reject solutions that make any log input negative. All right, so we will reject any solutions from step three that will create a negative number in any of the logarithms. All right, good. Very good. So we just have a few examples and we will be done for tonight. All right, example. So let's solve log of x minus 1 is equal to log of 8. Okay, good. So firstly, we have a single log on both sides. So step one has already been completed for us. So let me just write that. Okay, so step two is we can set the inputs equal to each other. So set the inputs equal to each other and solve. So the inputs here are x minus 1 and 8. So those are the things that you set equal to each other. So x minus 1 will be equal to 8. Okay, and of course you can just add 1 to both sides here and you'll get that x is 9. Good, so let me just do a quick mental check that x equals 9 does not create a negative anywhere. No, it doesn't. So if I substitute 9 into the left side, I get log of 8. And I can't substitute x in on the right side. So good, checks off. Okay, next example. Log of 3x minus 2 plus log of 2 is equal to log of x plus 4. Okay, so we need to look at the steps. We need to write the left side as one log. So we need to get it into log of something equals log of the other. So we can actually use the product rule on the left side. So we can smash those logs together as log of a product. Okay, so the left side can be rewritten as log of 3x minus 2 times 2. Okay, and that is still equal to log of x plus 4. Okay, so I hope, so just let me know, is everyone okay with going from the first line to the second line? I am just using that product rule to rewrite the left side as one logarithm, so you have to multiply the inputs together. I multiply 3x minus 2 by 2. Good. Okay, now use 1, 1 property. So now we're in good shape. Good, so we set the inputs equal to each other. All right, excellent. So I can just bring the 2 in front of the parentheses because the order of multiplication doesn't matter. This is 2 times 3x minus 2 is equal to x plus 4. Very good. So you can solve this. You will get x is equal to 8 over 5. All right, so just check this, please. All right, so that's just a linear equation. So I think we're all okay on solving those. All right. So just check. Okay, now let me just do the mental check that this won't create any negatives. Okay, so 3 times 8 over 5, that will be 24 over 5 minus 2. 24 over 5 is greater than 2, so it will not create a negative there. And then on the right side, I'll have log of 8 over 5 plus 4. That's a positive number, so you're good to go. So this checks. This won't create any negatives. All right, last example, kind of a fun one. So example, natural log of x plus natural log of x is equal to natural log of 2x plus 3. Okay. Okay, again, we need to make the left side one logarithm, okay? So let me use that product rule again. So this left side will be natural log of x squared, okay? Multiply the inputs, x times x is x squared. That will be natural log of, that will be equal to natural log of 2x plus 3. So everyone okay with this step? Good. Now use 1-to-1 property. So we have one log of the same base on both sides. I can set x squared to be equal to 2x plus 3. Very cool. And now we are in the situation of solving a quadratic. All right, so this is another thing that we know how to do. So that's kind of nice. So let me just quickly run through solving this quadratic. So you bring everything to the left side. You get x squared minus 2x minus 3 is equal to 0. And here we're going to do that quadratic with leading coefficient of 1. You find two numbers that add to -2 and multiply to -3. The numbers that work here are -3 and positive 1. -3 and positive 1. So this would be x minus 3 times x plus 1 is equal to 0. All right, this is all familiar stuff. And then next, we use one of my favorite properties, the zero product property. We set each factor equal to 0 and solve. So you just do that in your head. You get that x is equal to 3 or x is equal to -1. Okay, now we need to go back and check, do we get any negatives now if we plug in these solutions? Let me start with 3. If I plug in 3, so you have to go back to the original equation. You get ln of 3 plus ln of 3, all good there, equals ln of 2 times 3, which is 6, plus 3, which is 9, ln of 9. You're good. Okay, so this works. How about -1? Well, look what happens immediately. I will get ln of -1 plus ln of -1. No good. So that creates a -1 in the input of the logarithm. So I really want to just be explicit. X equals -1 causes natural log of -1. I mean, I don't even feel right writing this expression. It just is so wrong. I feel dirty writing this, honestly. Just kidding. Causes ln of -1 on the left side. So you reject. All right, so I'm just gonna kind of just cross it out. It's no good. All right, so I'm gonna, to make this a little better, I'm just put quotes around this ln of -1 because it's not really a true statement. All right, so the answer is just x equals 3. All right,